Hi everyone, this is Harsh, and today we will going to implement this Qwen 3.5 architecture from scratch. So this is Qwen 3 diagram, and thanks to Sebastian because he created amazing diagrams. This one is Qwen 3. I have Qwen 3.51, but like it's this one. But it's basically it is the bigger one with MOE architecture. We will going to implement Qwen 3.5 2 billion parameter model, and which resonates to this one. It's more of like a, you can actually understand much better here, but all things are exactly same. It is just that instead of like self attention, we also have gated delta net attention in Qwen 3.5. It's like a upgrade version of it. It's basically a new kind of linear attention, which is more efficient because self attention is goes and look up every kind of everything, every token, but gated delta net doesn't look up to every key value, kv thing. Rather, it's much more efficient, and it is designed for like long context understanding. It has various linear units which basically adapts to what needs to forget information, what needs to adapt. And it's really more complicated, I would say. This is exactly like this, but it works with self attention and linear attention. So some transformer layers will have like a linear attention, and some transformer layers will have the gated attention. So this is basically, you can see like gated delta attention or gated attention. So gated attention, it's exactly like self attention, but like it has one more linear layer, which is like a gate, and this gets multiplied after the scale dot product. And then we have like gated delta net, which is more of a complex thing. That's what I was talking about, and it has multiple linear layers. This has the gate, and this is the gamma beta thing, and this is the V, and QKR works in a pair here. So this is basically like that. So we can actually look at like how overview of it, and then we can start implementing right from there. So this is tokenized text. We get tokenized text, and then we tokenize the embedding, and then we will enter into our decoder. This is the blue part is the decoder. So the first is that it takes out the residual part, and then it's added after the attention. So the residual parts we take out, and then the hidden states gets to attend the RMS norm. It computes the normalization, and then the attention, which could be linear attention or full attention, and then we have like we compute the residual, we add the residual, and again there's another residual after this thing, which is like a more, we don't have attention there, but just a MLP, which is like feed forward. Before that we have RMS norm, and this is and then the residual get added. So this is basically two residuals in the decoder, and this blue thing is the decoder, the whole thing, the whole blue thing. After that, like after getting out from this decoder part, we have this final RMS norm, and then the output layer, and that's it. So this decoder is basically can have like multiple layers, like 8 layers, 12 layers usually have. We will have a configuration of it, and we can look at those things. But like this is what the feed forward is like. It's just linear layers, CDU activations, and there are another linear layers and stuff. But the main thing we need to implement is that the masked, this one, wait, let me go to here, gated delta net or gated attention. Two things we need to implement, these two architectures. And we need to implement the RMS norm. They have like a different kind of normalization stuff, because like we can use the same normalization of the pytorch one, but I don't like the formulas they have like different. And I found like the original implementation of this model has kind of a different RMS norm, so we can implement those things. I hope I'm recording right now, and all the things are like recorded. I hope all the things are getting recorded, and my voice is clear, because many times I record and voice doesn't record. So that's the very hard feeling from when it happens. But I hope everything is fine in recording. So this is basically what we need to do. Let's start implementing. So this is where we need to implement, and I have actually just put the some formulas here because we don't need to actually memorize those formulas. It's going to be used in gated delta net. This is beta and gamma. G is the same thing. Wait, this thing. So gamma and beta, and this has some formula. So I just put the here, and this is basically some, again, like some kind of like log stuff, and DT bias is getting used in this formulas. So the more complicated architecture in this whole Qwen 3.5 is the gated delta net, and then all other things. Attention is, I hope you are familiar with attention, self-attention, and the how like LLMs works. And another thing we need to implement is rope, which is rotary positional embedding, which is going to be added in the gated delta net. And sorry, not gated delta net, but gated attention. We don't have any kind of like positional understanding in gated delta net. We just like, so there's no rope, but it has and uses in the gated attention. And that gated attention is basically, so Q and V are the two, Q and K, sorry, Q and K, query and key value, basically, because they are more of like a much like input. So those two things needs to have understanding of the positions of it. That's why like we add understanding of the positions, and that positions can be are learnable, and that's why we implement rope, which is a which is a rotational positional embedding, which is basically rotates. So I can just show you like this. We can actually look at more when we will going to implement the rope thing, but now sketch out our whole thing first, because the first thing we need to do is like just sketch out the whole architecture. So this is the stuff, like imported stuff, nothing fancy. The first is we're going to implement the RMS norm. So in here, basically we don't have that much of thing to implement, but this will take like a dimension, and what else? It will take like EPS, which is going to be added. So I will like tell you like what exactly the RMS formula is, but it is also int and 1e, sorry, 1e minus 6. So this is the value of it. It's the default value. So right now just need to sketch out all the things, so just we can leave like this here. Then we will make the self attention. So before that we can implement rope. This will take config. I hope it's recording. I hope you're recording. Right. Then we have a little more space for the screen. Right. So rope is kind of a thing, right? Then so it will have like super. Then we have like self attention. It's why we are doing like this. We can just copy this attention, and we have then gated delta net. This gated delta net, basically has many different things, like many linear architectures. It will go like it's something is unique architecture you're probably gonna see. And then we have like decoder. Then inside, after decoder, we also need to implement cache. So we will also take a look at like how cache management actually do here, because because in inference, I'm not going to optimize this for like how exactly the original version, the optimized version is. I just need to actually make it like how we can implement this architecture, but like also make sure that the cache management is right, and we are making sure that the past tokens values get cached, and like have efficient kind of forward pass during the inference and stuff. In the end, I probably going to load the actual weights of Qwen 3.5, and then we can see how this is working, how this architecture is working, and prompted some little things. Although like I have just kind of I'm worried about like, because we're going to implement our own way, like the variables names and the weights names is different, so it's won't going to be like it cannot load the weights. It will mismatch the weights. So what I can just like do, I can figure it out. We can just figure it out in that. So let's go. So cache, dynamic cache. Then we have text model. Text model is basically the last version of it. That's it, I think. That's all we need here. We need to just implement these architectures, and we are done with like Qwen 3.5. We can actually run the architecture. So the first is RMS norm. You probably heard of this norm, but it's like they have a kind of a different, what I felt, maybe like it's kind of same, but it's first we need to first we need to do is like define some things. So weight, which is the nn dot parameter, nn dot zeros, and this will going to be dim, yeah. Self dot, then this is the formula we need to implement. X is dot tensor return. X is x multiplied by self dot, wait, it's dot square root. So we take the square root. I think RMS has this, yeah, RMS has this kind of stuff, but like, so this formula is exactly like this, but this gets multiplied by x also. So it gets EPS as epsilon is getting add after the summation, the mean of it. So this is the mean. We calculate the mean, then add the epsilon. This is the whole normalization stuff. So dot square root x dot power of 2, then dot mean in the last dimension, keep the dimension please, and then add EPS, then just add it, return x. This is the whole thing to make sure it's float. Then we have forward. That forward basically just takes the same thing, x, which is a tensor. That x is self dot, instead of x we can just say out dot norm, yeah, return out. That's it. This is all. This is the entire RMS norm we need to implement, and we can actually test it. How we can test this? We can go if main equals to main, then we have to do norm RMS norm. The dimension is, let's suppose we have this 64 dimension. APS is kind of a default we can use. Then we have out equals to norm dot random. Let's suppose batch size is 4, because we will going to pass the actual hidden states. So batch size, sequence length, and hidden size, it will have the dimension. So batch size is 4, sequence length will be 20, and then the end thing, the yeah, 64, sorry, this, and then we can actually out dot shape python, wait, we have this, yeah. So exact shape we are getting in from the norm. So it's working, it's getting normalized. We can just look at it, but you probably not gonna understand what exactly is the how this is got normalized. But yeah, so the next thing is we have to implement the rope. You're recording, right? I hope you're recording. Don't mess up, because this is the second time I'm recording. Actually, the first one, the audio stopped. I don't know like how it happened. So rope. So I had like a really good article about understanding of the rope. Rope is this kind of thing, like this is how it works. Like it's basically rotational embedding, which help the model to understand the positions of each tokens. So let's suppose my name is Hirsch, and Hirsch eating apples, and apples eating Hirsch. Like these are two completely different things. But like if model just understand the embeddings of the tokens, the Hirsch is noun, apples is a kind of a fruit, and so the model will understand the meaning of the words, but not the understanding of the sentences if they don't focus on positions. And that's what the positional embedding do. They basically creates a frequency with position IDs, and that frequency determines like which position had kind of a different frequency, have different kind of meanings with the positions. So in a nutshell, rope is basically the works with frequency of each token. So, and that frequency is decided by the how they are rotated in a sequence, and that rotation is computed through functions which are very famous, cos and sine. Although like this rope is kind of a very modern way to compute the positional embedding. We had earlier, we used to have the sinusoidal way, which is like a non-learnable parameter thing, but this one is learnable parameters because it have like a inverse frequency. That inverse frequency will learn at each step of training the differences of the words and stuff. So I think in ChatGPT, I think I have asked many things about this. So the formula to use this to compute this inverse frequency, which is like the 1 by base of 2i by d. So what we need to do is like we will get like the hidden states. That hidden state might be q, query, and key, and we need to matrix multiply this with inverse frequency so they get rotated. So they rotate itself with given this inverse frequency, given when applied with like cos and sine. So when they get rotated, they have the initially they will like a random rotation, but like as the model will learn, they have the they will rotate in a more better way where they understand each of the words in a sequence. So this is the formula we need to implement: inverse frequency 1 by the base of 2i divided by d. And it's not that hard to implement. We can just go and we can just say, first we need to actually compute the theta, because that theta is more, the theta is basically this p is the rotational factor thing, and then inverse frequency. Wait, this stuff is different. And then after computing the frequency, we need to compute the cos functions and sine functions and apply to the our Qwen, query and key. So yeah, that rope basically. So self dot theta config dot theta multiply by self dot positional rotary function. There's some rotary factor which, like in the original implementation, I saw that this had some values, but like we can pass one here right now. 1.0 self dot dimension is basically, config size. Hello, it's recording. Well, this theta then can be used. Theta is a base, theta is just a base here, base. And then we have to like compute the inverse 1 by base and then 2id. So self dot inverse frequency is 1.0, and that is applied here sorry, self dot theta the power of dot arrange. That arrange basically will create a sequence. So let's suppose if we want to compute 0 to 10, so it will take 0 to 10 and then 0 1 2 3 4 5 10. It will give us the sequence in a tensor. So this would go to till the dimension of it, but it's the twice of it. So because so we need to make sure that it's take that twice jump of it while creating the sequence, and then it's get divided by self dot dimension 2. You can see like dimension divided by d. And I hope this, it's not hidden size, it's the head dimension, because that dimension is basically the query and stuff, or it's going to be head dimensions. It's not a hidden size. Hidden size is basically because our attention, self attention, will divide into multiple headed attention, as you know, multi-head attention stuff. And then so we also only need to consider about the head attention here, right? So this is the inverse frequency divided by self dot dimension. That's it. That's all we need. I think we also need normalization stuff. No, we don't need normalization stuff. Yeah, I don't think like we need normalization here. Position, no. So self, well, we can also to make it more optimized, we can actually do something like this dot register this buffer, because otherwise like it will gonna take a lot of memory here. It's the theta could be like this value and to the power of this. But let's suppose to make it more simplified rather than more optimized implementation right now, we can just like leave that thing. Then we have this x dot tensor, position IDs dot tensor. These are the two things we will get, and it will have like hidden states. Sorry, x is hidden. That is bath size, sequence length, and x will have, but like it will have like some kind of dimension, the query dimension, which like number of heads, and sequence length, head dimension. Because the whole point of this rope, like this initialization of the rope module, is that it the multiplication will happen between inverse frequency and the position IDs. It's not, we don't need like x stuff here, because we separately we will create a function where we will apply. But okay, we can pass because we need some like what what is the D type and stuff. So this is X, this is X, and that X is basically self dot, wait, position IDs, badge, sequence length. Then this position IDs basically needs to be matrix multiplied with this one, and that has a shape of, wait, that has a shape of dimension half of it, right? So we need to make sure that the position IDs has a shape where these two can actually matrix multiply and create some kind of a learning stuff. So they learn stuff, learn the representation, learn the frequency, and all the things. So position IDs, we need to just make sure that position IDs dot none and then dot expand. So this will create an unsqueeze of it. It will unsqueeze this, and then the rest of dimension will be same. Then we have to do is like expand. So the expand will actually fill out all the things we need to do. So this is should be 3. The 3 should be why, because the position ID, the positional embedding of the Qwen is not just one medium. It not applied in the one medium like only text, but it has multiple dimension, multiple mediums like images and audios and all the stuff. So it has 3, like original implementation, you will see like it has 3 different positional embedding. So this is what exactly we will going to do. The first is going to be 3. Well, after that, all 3 going to be interleaved into one. So we will see like how we can actually interleave into one, because that won't make sense if we just like, that won't really going to matrix multiply with this 3. So we need to interleave into one. The second dimension is basically position IDs of shape, which is the batch size, and then we can just say -1, so it will figure it out on. The position IDs now will have 3 batch and sequence length, right? So, and inverse frequency, now we need to just make sure also inverse frequency have the same kind of a dimension dot inverse frequency. Although like we need to make sure that it has like a 4 dimensions. So the first should be just make none, none, and then none. So dot expand. So I will explain in a moment that what exactly is this and what's the shape of this. So this is like this create a 1 1, and then the dimension, which is like the information of the whole inverse frequency will be in the 0 1 2 second dimension of this second index of this inverse frequency, and then we can expand this. So expand, we can similar do the similar thing 3, and position IDs, we can take a help of position IDs shape first, which is batch size, position ID, and then the third one is like -1, which is like just use the same thing, and the last one should be 1, right? So it will have a shape of batch size, sorry, 3 batch size, sequence length, and sorry, not sequence length but dimension, sorry, what, yeah, dimension, and then 1. So this is the shape of it, inverse frequency. And then we can actually go and implement, like do the matrix multiplication, I guess. So frequency, inverse frequency at the rate self dot position IDs. Make sure, we need to make sure that it has 4 dimension. So so it will have like the last, wait, none, this, and this. So this will create like the first 0th dimension is kind of the same. Why I'm saying 0th dimension, like the first dimension is the same, second dimension is okay. So in the 0th dimension we have like the same thing, the first dimension we have same thing, and then it's none here, because just expand the second one, the last one has the same thing. So I can explain you here a more better way. 3 batch 1, then it will going to matrix multiply with 3 batch sequence length and 1 1 and sequence length. So the resulting thing will be 3 and batch will be exactly going to be same, because the last 2 dimension is more matters, because last 2 dimension going to be multiplied, others won't get affected here. So 3 batch, and then we have dimension of 2 and sequence length, because 1 1 going to be multiplied, and then it will have sequence length. Okay, now we need to actually do the transpose, because frequency dot transpose. This should be dimension, should be the last here, right? So I have to 2 and 3. This we're going to transpose it. So sequence length is going to be here and the dimension is going to be here. I'm not sure, I have to make contiguous here. So this will have a dimension of, okay. But the problem is that we cannot like just return here with the 3 because we need to make it interleaved. We need to make like the final thing should be batch, final output should be, so it goes with the flow, should be batch, sequence length, and dimension. So this should be the final output. So that's why like I am going to use a function which is like I took from Hugging Face and apply envelope, something like that was interleave envelope and frequency. So this will turn batch, sequence length, and dimension divided by 2. Now it's still we have like the half of it, so we can just make a pair of it. So, and also the rotational positional embeddings works with pairs. So we can just concatenate frequency, dimension. If you want to understand why we are doing it, we can just ask the same thing, same question here. -1. The dimension should be the last, right? So it would have this kind of a shape. The same thing. Frequency contains one angle per pair. Then we duplicate it to match the full dimension. Here dimension. Frequency is only the half the dimension because each frequency corresponds to one 2D pair. Because each frequency correspond to one 2D pair. But the actual query key vector has full dimension, not this. That's why I expand this and cos have the same shape. First half interacts with the second half, or odd even pair interact depending on implementation. So it's like a kind of a thing because the half gets like half the same. So the first half interact with the second half, and or even odd pairs interact depending on implementation stuff, the dimension we wanted. And this rope basically returns the sinusoidal and cos functions. They are just like they don't return the frequency, but frequency is the way to compute the frequency is a way we can use to compute the cos and sinusoidal function. So we can just say embedding. This is the position embedding. That embedding is return embedding dot cos d type is d type x. So in the whole point of that x I basically passed here because I just wanted to make sure that it has a right d type. And then embed dot sign, it should be like this. Nice. We can just test out this rope thing quickly. We can just say position IDs is dot ones from 0 to 20, right? Dot expand with the batch size. Let's suppose the batch size is 4. We can just define batch size here, not a problem. Batch size is 20, something like that. Batch size and -1. Okay. Position IDs, this is position IDs, and rope is rope. Config. Okay, so we lack config. So what I have just done is like, I've already created a simple config. So we can just like from config import config. It's basically a simple config using simple namespace, which has like vocab size and all the required things. The actual Qwen 2 billion model has the exact configurations. I just put that into a simple config, so we can use from here directly. I hope it's, yeah. And yeah, rope. Then we can actually out equals to rope, and axis x can be anything. Dot and 420 batch size. That should be 4 batch size 20 sequence length, and then we can just replace this with sequence length, and hidden shards can be 128, and then position IDs we already defined it. Okay, I see it's working, but like it has some kind of, this one is working, but this one is not working. It has this torch dot ones. Wait, torch dot one. It should be batch size torch dot arrange. Yeah, it's okay. So we can just say float. Nice, it's working now. So it will have like a 2 tensor. It will in a tuple, which is like a cos and sine. Okay, so we have implemented rope. The next thing we have to implement is self-attention. Next, we have to implement self-attention. So let's go. I think it's not that it's exactly the kind of the same you have seen if you have read the self attention is all you need paper. So the computation of attention, the formula is kind of the same, but it just kind of divides into heads, and we have to just make sure the shapes are right and all stuff. So it connects each and every dots to those computations. So the first is that just define hidden size and stuff, like dot self dot head dimension, which is the same, right? Head dimension self dot number of attention heads. So this kind of stuff is different. Like this attention is not exactly the computation of attention is same, but the it's called grouped query attention, basically where you have multiple heads. Like, I hope it works. Okay, so where you basically have this multiple heads, you have multiple values, multiple keys, multiple queries each. And basically if you have 10 heads, then 10 heads will have 10 queries, 10 keys, 10 values. But in grouped query, it's much more different. It's different than the multi-head attention, because we have this multiple more number of query heads but fewer key and value heads, where like the multiple query heads linked to those few key and value heads. So like you can see here, like this 1 2 3 4 5 6 7 8 heads are there, but like the two heads are connected to the same keys and value. So it's same keys and value, they are connected. So this is exactly what Qwen 3.5 has, that it will have like in multiple query heads, but like a fewer key heads. But in the nutshell, they will exactly look like this, like in computation. And if you expand the graph, if you expand the tensors, then they will look like this. It's just like they have the same value, because we will just repeat the values of it. you know right now in multi-head attention, you have like each query has each keys value. So like all these key heads are have different tensors. But but in grouped query key, it will have like some of them have the same kind of keys, some of them have same kind of keys. So if here you can see like these two query has same kind of keys. It's not that the heads are less. Heads going to be the same for us to compute the attention, uh, but it's just like they have same values repeated afterwards. So this is the grouped query attention. There is another type of thing, which is multi-query, but we don't have to implement this, so we can just leave there. We can learn about from this what we call KLU. Okay, anyways, so config dot number of attention heads, it should be heads, self dot number of kv heads, config dot kv heads, and self dot. Okay, and then we have this normalization q norm RMS norm, which will have like a self dot head dimension, config dot RMS norm EPS. Then we have K norm, which is kind of the same, right? Then we will define our query, which is a linear. So you can see like the architecture here, this thing, linear Q, K, B. The Q and K have the RMS norms. And then we have a gate. So the gate is basically, it's not something we will define differently. In here it's like defined differently, but like it just comes out from the queue, what I have seen in the implementation, the original implementation. So in the linear int feature is basically self dot hidden size. The hidden size will come, and then it will get number of attention heads multiplied by self dot head dimension, and the twice of it, because we will extract the gate from the queue itself. So we can just say queue projection instead of queue. Then we have k, and then dot linear, this will have hidden size, then self dot number of kv heads multiplied by self dot head dimension. We need to also make sure that we pass the bias as config dot attention bias, right? So it will have like a different heads. So number of kb heads, and then number of then we have this v. We think will have the same kind of initialization. One more thing we need to compute, because they have different heads. So self dot number of kv groups, it can be calculated as number of attention heads divided by self dot number of kv heads, and this will compute the groups of it, right? So now we have to, I hope it's recording. Hello. Yeah, now we have to then project out. So project, or we can select project out. Why I'm like taking care of the names, but anyways, linear self dot number of attention heads, self dot head dem, then it will spit out the hidden size. It will have the same kind of attention bias. That's it. I think that's the initialization of the self attention. Now we can just forward, and forward we will get like, first is hidden states, which is attention, which is tensor, then attention mask, which is also a tensor, but like it can be none also. And then we can get position IDs. Position IDs is the tuple, which position embeddings we will get, not position IDs. Like a tuple. Okay, it should be here. Then we will, there's also cache. So cache. This cache is basically going to be none, and we can pass through self attention. So the hidden states will have batch, sequence length, and hidden size, right? And position embeddings will have batch, sequence length. It's a tuple, so like they have cause and sign, so sequence length and position dimension. And attention mask, if present, then it will have a batch, sequence length, batch, number of heads, and query length and kv length. This will have this. We can also say causal mask as an attention mask. So hidden state, batch size, sequence length, self dot state dot shape, right? And that shape is basically, we can transform self dot, wait, linear, just do the projection. Q projection is self dot q projection hidden states, and then it will have a shape of like the double sides of it, which is like 2x. So what we can do, we can q and gate q projection dot chunk, that will chunk out the q projection. The torch dot chunk should be torch dot chunk q projection into 2, right? And then we have this, the last dimension. Then we can actually, and gate should have a, like a gate dot reshape batch size sequence length -1, because gate will be like multiplied here. It will going to multiply here after the scaled product attention. So it should have this kind of shape, right? And then q will be q dot reshape q batch size dot number of attention heads, because we need to divide it into heads, because as we have seen in our here grouped query, that we need to divide it into multiple heads, and the query will be divided into its own heads, like which defines the number of attention heads, and that key and value will be divided in their own heads, which is like defined as number of kv heads. So this number of attention heads, and then first is sequence length, number of attention heads, and then self dot head dimension, right? Then what you do is you transpose it, right? To actually make this sequence length there to here, because we need batch size, attention heads, and then sequence length and a head dimension. So for that, we can just do is transpose 1 and 2. That will basically make the batch size, sequence length, number of heads, attention heads, sequence length, and head dimension. K dot reshape. Why we are doing reshape? If we haven't actually passed the forward, we haven't did the forward pass, and I've started doing reshaping. So self.k hidden states, then reshape batch size, sequence length, self dot number of kv heads, and head dimension, then transpose, and just we can say it as a v. Nice. So now we have a proper shapes of q, k, v, and what we have forgot is like before transpose, like we can actually do this thing. I'm not sure like it should be after transpose or like before transpose, this thing, the normalization, RMS norm, but let's go with like before transpose. And because it won't much matter because it will be applied in the last head dimension. Self dot k norm, self dot k norm, but that's like very little subtle details. Like you can find out like, okay, it should be applied after the transpose, the q norm, or before the transpose. That makes it confusing. Sometimes you even read papers or look at the architecture. But I guess like in the original implementation they have, in the Qwen 3.5 they have used it before the transpose. So this is the actual shape. We have progressed till now. We are here right now. Now we have to do some caching stuff. So caching stuff is basically is important here. And before caching stuff, there's positional embedding, because we have to apply this positional embedding to the our attention, and that attention will go in QK, that QK RMS norms. So POS, positional cos sine positional embedding, and you get Q, you get K. Apply positional, apply rotary position embedding. We haven't implemented yet, but this is basic. This will take Q, K, cos, and sine, and it's time to actually stop here and then implement, because we haven't implemented that this apply rotary positional embedding. We have just like defined, okay, how like the forward pass of it, the learnable parameters things, but we haven't like used it like we cannot like used it in our q and key. So there's a function we can say apply by rotary position embedding, and that takes q, k, cos, sine, right? And that q has a shape of this, q will have a shape of this, and cos will have a shape of, cos, q has a shape of this, cos has a shape of batch size, sequence length, and position dimension. So these two can be different, head dimension, position dimension. So like how originally how they have applied the positional embedding to the query and key is that they took out some parts of it from query and key till the position embedding, position dimension, and only applies to that part. They haven't like did some kind of hello. So this is what we going to do. Like we take some small part of it, of the query and position, query and key till this till the position and dimension, and then only apply that thing, we rather than the whole sequence length. So we can say like till the sequence 3 dimension cos dot shape. And notice here that we have number of heads here, but we don't have anything here, so we need to make sure that we unsqueeze this. So cos dot unsqueeze, squeeze the first dimension 0 first, and again on this side. So this will have, right? Now we need to just to take out the small part of it and apply the only the last dimension. So q rot, which is the q rot and q pass. Q rot is basically the where we need to apply the rotary, and pass is where we just need to leave it. So q rot, q, same goes for this k pass, k rot, right? We did a mistake. It should be like this. Now the thing is that return q. Now here's the formula, basically how to apply this thing. So this is the formula basically where you do the cos theta and then you apply to it this, and you take, these are the two matrices, And then 2 matrix is basically, wait, this is not the same formula. What I was looking for, I think just ask it the for what to apply to first embedding. Yeah, this one is x rope x dot product to cos, and then plus rotate half, and then sine. So the rotate half is basically we just rotate half the entire matrix and then just add this thing. So these are to basically get summed this, right? So this is what exactly we need to implement. Before that, we need to make sure that we have rotation function. So rotate half is where we have x as a tensor, and then we divide into x1 and x2, and x1 and x2 can be divided as x as a, it will be divided into as a last dimension. So x dot shape, right? And to rotate that, the matrix 90 degree, you have to rotate it to the 90 degree, negatively 90 degree basically. So y charge degree is kind of, yeah, by itself effectively 90 degree of the paired components, but rope as a whole fixed. So what is rotate? 90 degree clockwise rotation and 2D. So this is basically, this will create like a 90 degree clockwise, counterclockwise rotation. So x minus x2, x1, right? Minus x1 torch dot cat in the last dimension. That's it. We have implemented rotate half, and we can just use it. So q embed q rot multiply by cos, and just make it into bracket, plus rotate half q rot rotate half q rot and sine k embed. That's it. It should be k. Now we have computed, just making sure everything is right. Q rot q pass Rotary dimension. Hello. So q embedding. Yeah, so everything is right. And what else we need to do is like, we need to make sure that things we have like divided, we just concatenate into one again. So the return should be, q is basically torch dot cat q embed and q pass in last dimension, and exactly here also q embed k pass last dimension. Then return this q and k. That's it. This is applied. This, we have applied the Rotary positional embedding here, and we can use this here. So after applying this Rotary positional embedding, what we need to do is we need to what do we need to do? Yes, let's look at the architecture. What we need to do. So token embedding this QKV after that. Okay, then that's it. Like, we need to compute the attention mechanism, which is, we can find here, scale dot product attention. So yeah, but I mentioned also that we need to do some caching stuff. So if cache is not none, then what is here is that we can put the query and key and value in the cache. So k and v is cache dot date k and v. That's it, I think. Cache, this will basically put into this key and value, so it can be used later and can be used for calculating the sequence lengths. Okay, how much we have used, what exactly in our, what is the state of key and value if you're like conversating with the model and stuff, because we know we have some past scene tokens, so it will help us to basically compute the length of the position, length of the key value and key and value. That's it. Right now, then we can just compute attention here, and it's exactly the same what we have seen or like read in the all you need is attention, and attention is all you need actually. So we can do attention weights and self dot attention torch dot mat mul. This will compute q and k, and we need to transpose this, so it can do the matrix multiplication, and then after that we need to apply scaling. So I don't think we have defined scaling here, so we can just define it. Self dot head dimension minus 0.5, right? And before softmax, we need to add and use our attention mask, which basically going to be causal mask. So if attention mask is not none, self dot attention weights plus attention mask, right? Then we can do attention mask is added here, attention f dot softmax. Then we can compute the attention softmax. That's it. Then we have to do is like attention output is dot matmul again, attention out. It again should be like attention weight. Sorry, not attention out, because till this soft max it's attention weight, and then after like you complete the matrix multiplication with v, it's going to be the attention output. So we here right now this will have like query kv length. So this has like query and kv length dimension. The last dimension, last two dimension will be query length to the kv length. That's why like it got added in here, and then it, after doing this, it can get back, but we need to again transpose this. So like it will have the batch sequence length, number of heads, dimension, and sequence length. Wait, I think I'm doing a mistake here. That you know it's not, we don't need to actually transpose it here, because it will have the exact dimension what we needed, so we don't need to transpose it. Yeah, but we will transpose this after this. So batch size this, and number of attention heads. Wait, I'm being confused here. Batch size, number of heads, sequence length, and dimension. To make to make the back to get back the shape, we need to just pull back the sequence length and number of heads here. Okay, and then we can just multiply number of heads in dimension. Okay, that makes sense. And attention output are t-shape, number of heads, sequence length. Okay, so then it will have like a sequence length here and number of heads here. So batch sequence length, and we need to make sure that sequence length and then hidden size, batch size, sequence length, and then hidden size -1. Okay, nice. And attention output can be, attention output highlight with gate. Sorry, f dot sigmoid, it should be sigmoid gate. Okay, and then we can just do out projection. Out self dot out project out attention return. Awesome. So this is the self attention is implemented here. Well, we can test here. Tension config tension. We need to pass the hidden states. So hidden states, we can define hidden states here. Hidden state positional embedding dot random dot batch size sequence length, and let's go with like 128 only, right? What was the batch size and positional dimension? Okay, nice. So we can pass the position embedding and attention mask. Attention mask is just going to be dot once, and that is also batch size and sequence length. But we have like a wait, this dot once, it's a different attention mask. It's not that attention mask. So sequence length, we can leave the attention mask here. When you will implement the whole text model, then we can obviously pass. So let's test with this out dot shape. Okay, kv heads, number of kv heads, it's number of k heads. What it had, wait, let me see the config. Number of key value heads it is. Okay, now test this. Nice, it's linear, right? Lot of mistakes we have done, lot of mistakes. It should be like this. Cos 22 32 must be 108. The size of a tensor of 32, we need to actually make sure what's wrong. So we can just print out q dot shape, cos dot shape. Okay, so q is 32 and this is 128. That is because it should be 32 also, because it should be divided by the heads. Yeah, right. So instead of like we are actually testing with random numbers, we can just use the self dot hidden size config dot, because we already have all the stuff there, hidden size, and or hidden size divided by dot hidden number of attention heads. Oh, wait, okay, instead of this, okay, so instead of random numbers we can just pass like config dot hidden size and config dot head dimension, which can actually help us. But I'm getting new error right now. It's like the problem is with what we are doing in here, and the problem is that sine equals to cos. How can it be? It cannot be like this, you know. So it should be sine, and then not. Let's see. Okay, again some error. Okay, so this error is legit because, you know, as I mentioned, we just created different heads. We created different heads, but like those query has like this amount of stuff and this amount of heads, and key has less amount of heads and all these stuff. So but because when we do matrix multiplication we cannot have like same kind of things, you know. We need to have the same kind of thing. That's why then it will work, you know. Number of heads should be same as query has, as k has. So we need to just repeat the heads. It will not going to be have different heads for each different query, but like they're going to be repeated. So the easiest way to do so is to k equals to k dot repeat interleave, and number of repeats is, that's why we have defined number of groups, and the dimension should be second, because we need just to number of heads. It should be 2 or it should be 1. It should be 1 because number of heads. Okay, yeah, number of heads. Repeat interleave self dot number of KB groups and then number of 1. Now let's see. Awesome, this is working. So we have implemented the self attention. Now what we need to do is like the next step we need to take on. So the next step is gated delta net, which is more complex one, and this will take much more time. When we implement the gated delta net, the decoder is simpler one, and then we can continue from there. So yeah, let's go and implement gated delta net. We have like different kind of linear layers here. Linear layers, and then convolutional stuff. I can just say like self dot hidden size config dot hidden size number of k heads. So we have different kind of k heads here. So for that, like we need to make sure that we are assigning the right ones. Number of v heads config dot number of v heads self dot number of um number of k v, and then number of k dimension should be number of k heads number of v head dimension k head dimension and v dimension k head dimension. I think it's k head dimension. Yeah, head k dimension it is. Head k dimension, head v dimension. Okay, right, head v dimension. Then we can just change v dimension and dimension. So the dimension of k and v is just they have this the multiplication of number of heads and number of k dimension what they have. So because they have different kind of dimension even in each head, not like self attention we have the head dimension is each is fixed for all the heads. So here we have norm RMS norm self dot config PS's dimension is what kind of it should be okay QKV mixed. So because QKV the projection we are going to do is like a mixed of QKV. This is what I have seen in the original implementation where it is a linear, and then then we can actually extract QK and then V from here, where like each of three have different dimension and stuff. So self dot QKV, and then we have here hidden size. It will get a out project to con dimension. Why con dimension? Because because we need to do the convolutional steps. So it's just the number of k dimension, which is twice of it, and then self dot. This is the kind of con dimension is, and self dot con 1d going to be con and then dot 1d in channels groups. Kernel size we have to define the kernel size also. Linear con kernel size, then kernel size is kernel size, and then padding is basically 1 plus, and groups is also okay, it's -1, kernel size -1, bias is false, right? And then we have after convolutional, this will out projection, right? We have out projection, yes. That out projection is basically self dot number v dimension to the hidden size. Bias is false. Did I turn off? And then we have like number of linear layers, which is like qkv, right? Self dot, there's this b, wait, there's this z. I'll have to make sure that it has bias off. Okay, so linear, and then self dot hidden size. This is just a gated stuff, so that gated stuff should be like this false. And beta is basically, you know, it's just the other things, so it controls the, so basically all these linear layers, you know, this goes into gated delta rule, which we are not going to implement, but we are just making sure that it's implemented in the right order so it can be used, and then it can outputs the output. And self dot hidden size, then it takes like it's just the heads, so number of k heads, number of v heads, sorry, v heads bias. self dot a is hidden size v head. So this is the gated delta net stuff. In the forward we will get hidden states, which is a tensor, and attention mask, which can be none, and cache. And this cache, right, now that attention mask should be, you know, we need to multiply this like this, attention hidden attention mask, but we need to make sure that it has same kind of shapes, otherwise I messed up. So we know that hidden state can go to batch sequence length, and this will be the attention mask. So attention mask, attention, so we just like do this, okay, and then self dot mixed qkv paste this, yes, mixed qkv, and this will take hidden states, and that hidden state is, you know, have this batch size sequence length and content qkv. But because, you know, convolutional layer works in a different way, it needs channels, so it doesn't really matter what's the last dimension, it should have the right channels, and the column dimension should be in this first here in first dimension. So qkv dot transpose and 1 2, so this will have the convolution sequence length. Nice. Now what we need to do is we can chunk out this qkv into their own dimension, but before that we need to compute the convolutional layer. So self dot, and here's like stuff that actually qkv is like a transpose of these things 1 and 2. So if you want to compute the conv, you know, so conv padding, so we have to make sure that it has a right padding. So the next what we have to do is like to compute the convolutional stuff. So but if cache is none, we have to basically take out compute the cache. And so the next we have to do is like there's const state, which we will compute, but we will take out from the cache if the cache is available. So cache dot const state, I don't think like we have defined layer idx, right? Did we? I think we also haven't defined if cache is none in self attention. Yeah, yep, we need to pass the layer idx, which is the which layer it is, which because decoder will have like multiple, could be a 612 transformer decoders stacked, so that's why we will pass here layer idx also, similar to this one also, if cache is not none else. And there's one more thing, recurrent state, because the whole gated stuff is inspired by recurrent stuff. Like we probably have seen the recurrent neural network where we store the recurrent state, and exactly why we here do that because it's like a memory. It treat it like as a memory. Attention is also used as a memory, for which basically help us to do in context learning. But the gated delta net is kind of a new innovation that which help you to store the memory in a more efficient way, but it will be long context. If you have a long context, and it can generalize better, that that's why like it was defined in the first place. So cache dot constate self dot layer idx, if cache is not none, else not, it should be recurrent state. And if cache is not none, we gotta do is like we have to do pad and stuff basically. So pad conv pad max of either it's like which is max, so self dot kernel size minus self dot mixed qkb dot shape, qkb dot shape minus 2, which is like a sequence length. So we compute like, okay, if the sequence length is lesser than that, then we don't need padding, but if it's like very less, then we need padding, right? So const state f dot pad mixed, this will pad the const state. Here we have, I passed the qkb, sorry, it's not, it should be qkb itself. And right, then what we need to do is like we have computed the qkb, then we can go and qkb is then we can store this thing. So cache dot const state layer id equals to const state. So we have stored in the cache, and then what we have to do is use this thing, qkb equals to self.con 1d, and we have to just pass qkb, and this should be f dot value, right? Okay, this will spit out some kind of channels, but that's where we have to actually take the only what we need, which is the first is batch size, the second is count channel, which will be like the same because in channels out channels are same, but like the dimension, the last dimension going to be different. So we just need to do is like sequence length, that's it, and then transpose this 1 to 2, so we will have the again batch sequence length and condim. Now condim is basically the if you have, what we have defined is that self.kdim multiply by 2 plus self.vdim. So these two is qk and the third one is v. So we can just split these things, and qkv is dot split qkv self dot dimension we have to define. So k dimension, and self dot v dimension, right? There's no q dimension, but that's it, and there should be dimension last dimension. So we will have q, k, and v from here. Now we need to just reshape it. Q dot reshape it, batch size, sequence length, then number of k heads, self dot head k dimension, right? And k dot reshape, batch size, sequence length, self dot number of k heads, self dot k dimensions. Similar to v dot reshape, batch size, sequence length, self dot number of v heads, and self dot v head v dimensions, right? Now remember, we have defined some formulas here like this, and here we're going to use this. So we can just put somewhere here dt bias and alog stuff, and this is beta and g. So as beta is not defined, b is not defined, so what we have to do is like b is self dot b, which is what hidden state it takes, and it should have the shape of, b equals to reshape hidden states, sorry, batch size and -1. That's it. And not really, I guess it should, the b should not be like that. Wait, let me see. So So okay, so after convolutional and stuff, we applied celu and celu here and celu here and combined celu basically, and then we have splitted that gamma and beta should be you know self-dot beta. And I guess like in original implementation they had this kind of, let's define z first because z is our gate and that is more important. So self dot z hidden state, and that will have a path size, sequence length, and v dimension, right? V dimension, right? So this have the right shape here. And b, for the b, I think self dot b hidden state, this will spit out number of size and number of v heads, right? Okay, so this will have batch, sequence length, and number of v heads. Okay, now it makes sense, like it can actually compute these stuffs, but the g is g dot, I guess, like, so after that we have to compute the gated delta rule. So this is the gated delta rule, and this this thing is gated delta rule is we can just import it directly. I just like took it from Hugging Face, which give us recurrent state and core attention core gate torch gated recurrent. This one just need to pass query key value g beta and recurrent state if cache not none else. Okay, right, that will spit out the attention core. That attention core will go to attention core have a shape of like some weird stuff. Attention core, I guess. Then we have to do is flatten the stuff. Well, I don't know, like in original implementation why they had used they have flattened out and then they are computing did multiplying with the gate. But okay, let's we can do two. Attention core dot reshape minus one self dot v dimension. V dimension, and z is also z dot reshape minus one self dot v dimension. Z that is attention reshape bats prince and self dot project tension. Well, this still will not work because here we have different kinds of heads, so we still need to actually make sure that the heads are kind of the same, because number of v heads here is more than the number of k heads. So self dot, if you go to config, number of v heads, you will see v heads is 4, k heads is 2. So if number of v heads greater divided by self dot number of k heads greater than 1, then repeat is self dot number of v heads of number of k heads. This much we have to repeat, and again, like q is q dot repeat into and the repeats are rep dimension should be on the, I think, second verse, and k dot to leave rep dimension 1, right? And here the z should be z dot reshape bad size sequence length self dot b head v dimension. Okay, so this is gated delta net. We can test it out if it's working and what are the errors we are getting in here, right? So let's test it out right now. And it takes a hidden state attention mask. We have attention mask, right? Oh, we don't have. Okay, let's go with like hidden states dot boom. Wow. Okay, this one is we need to provide the attention mask. I guess like if it's not none, then it should be transposed. Okay, so invalid. We can take a help from codex, I guess, what we are doing wrong here. See one direct dimension bug in the delta layer. Okay, transposes because your value dimension is defined wrong. Okay, the value dimension we have defined is wrong, so we have to check value dimension. Value dimension is okay, this should be v heads, right? I see. And this should be, wait, it should be only 2 because we haven't transposed this, right? Awesome, this is working. Nice. Now let's check our progress. We have implemented RMS norm, gated delta net, and self attention net. What we have to do is like just implement the decoder, this thing, whole thing, like just stack, like create the whole thing, and then all good. Then we can actually we create this decoder, this blue box, and then use all these things what we have defined here, and then we create this big text model where we will define many decoders there, right? So self dot number of hidden layers, sorry, not number of hidden layers, but layer idx first, which define which decoder it is. Okay, so we have like self attention layer and full attention layer. So basically full attention is the self attention and linear attention is the gated delta net. So we have to define, like, because we have to use different modules for different use cases, and if the definition is defined as for full attention, then we have to use the full attention self attention. If the definition is defined for the linear attention, then we have to use gated delta net, right? So for that, I think self dot, we have this config dot number of hidden layers and self dot dx, we can just say dx. So if I go to config, you can see like layer types has this linear attention, full attention, all these stuff. So instead of number of hidden layers, I can just say layer types, right? And if self dot layer type is self full attention, linear attention, self dot linear attention is gated delta net, which will take config layer idea, else dot self attention gated delta net, sorry, self attention config dot layer idea, and that decoder probably has some kind of, it has two layer normalization layer. So self dot input layer norm RMS norm, which will have config dot hidden size will be config dot RMS norm EPS, and then post layer norm post attention norm config dot hidden size EPS is RMS config dot RMS norm EPS. That's it. That's the initialization of the decoder. And in the form we will have positional hidden state, positional embedding, we can just define as positional embeddings, and attention mask, yeah, attention mask, then cache, I guess. That's it. First is residual thing, because you know you have to take out this thing as a residuals, and then hidden states equals to self dot input layer norm hidden states, then hidden states equals to if self dot layer type equals to linear attention, right? Then self dot, then hidden state will be self dot linear attention, which will take hidden state, attention mask, and cache, right? Else hidden states will be self dot self attention, which will take hidden states, positional embedding, attention mask, and cache. But I think, you know, which type of attention mask it is. These two will have like different types of attention mask, you know, because these two will have like, you know, different types of, what I mean by different type, because this will have just a attention mask, and this will have causal attention mask, which is a different, which will be used in with query key, the computation of query and key. So I have to think about it, like hidden states. Okay, that thing we can do later, like differentiation of the causal mask, because when we will build the causal mask, we will use attention mask in a nutshell. Yeah, so this residuary, this will have like hidden state like this, then after computing the hidden states, just hidden state equals to hidden states plus this, that's the residual connection. Then we have another norm, but before that norm we are taking another residual. We can say like residuary like this, but okay, residual is also good. Residuary of the residual, isn't it? So residual, sorry, hidden state self dot post attention norm hidden state, and then hidden states equals to self dot hidden states dot. We have MLP. Wait, we haven't defined anyways. We can just define MLP quickly. MLP self dot. I think it's a small layer, so I can just pull up from the original implementation of it. So it will just gonna pull up from the somewhere I have implemented, but I need the better one. I have defined somewhere, I think here, this is the one. Yeah, but that was also good. It was not bad from there. Then we have hidden states, and then hidden state dot. That's it, I guess. State. Okay, so this is our decoder, and we can use decoder here. Decoder position embedding. Nice, it's working in one run. That's great. Now next is the last, not the last, but the dynamic cache we have to implement. But it's simple. In here we have to just define some things, which is recurrent state, which is going to be none for each layer. We are defining cache. So none for in the range of self dot. This would be self dot number of layers, which we config from hidden layers. Number of layers. Same with the state. I can just copy this and define constant. And here for the Q cache, K and B only. K and B, right? That's it. And we have here update function, which takes the query value and updates it. So if and layer idx, if x self dot k layer idx is none, then we will just like we can store directly like this. K, why it's q, it's k, and v dot k equals to, then we have to concatenate this thing. So I don't like why when I actually record in front of camera I just like misspell many words. Torch dot k is torch dot, yes, torch dot concatenate, right? K and q, okay. K, not like this actually. Self dot k layer idx and k, and you know the dimension, the last two. Why? Because it should be the sequence length the sequence we are storing. So that's why the concatenation will happen in the sequence. So let's suppose the sequence length is 20 and there's new things we need to update, so it will be concatenate in the sequence dimension. So the new tokens are like 5, so the total cache is 25 sequence, right? And here v layer idx self dot layer idx v dimensions to, that's why I haven't defined self. That's why I was saying like why it's have a different kind of colors, and then return it. Layer idx. My neck is paining right now. I don't know like how long we have been recording this. I think it must be like 3-4 hours, something like that. So I'm tired literally. But yeah, we are finishing this. It's almost done. Not yet. I think we have to do a lot of work still. So dynamic cache this is, and have like get sequence length, which is really interesting. So that get sequence length basically depends on the number of layers. It's like, you know, we just need to, this function will tell what is exactly the sequence length, which help us to understand, okay, how many pass tokens we have. Like, okay, we have 30 sequence already in the cache, so like the user is conversating, already have 2-3 question asked. Well, it cannot be 2-3 questions in 20 sequence, but I'm just assuming that it could. Then we need something like to tell, okay, this is what the sequence lengths are. So number of transformers layers, I guess. Yeah, transformers layers. Why we are saying transformers? Because like we are only going to take which has full attention. So for self dot, for I in range of self dot number of hidden layers, if self dot layer types I equals to, just return the I of it. Okay, so we can just say return the layers. Wait, not self dot, yeah, this comes in config, and
this will give us the sequence length. So it's simple, which is like we are just like indexing on k, and we need the index, so we just like took the first transformer layer, the 0th indection of it, and then just shaping it the -2, which is the sequence length, right? So this is our dynamic caching. Next is the last but not least, the text model. This will compromise everything whatever we have, and with that we can able to infer and do stuff like this. Is when we will implement this, we can say like, okay, we have implemented Qwen model and LLM. Okay, so it's also simple, it's not that complex. Self-taught number of hidden size, I can just redefine self-taught config, right? Rope is fig, self-taught layers is an module list. I hope it's recording. Yes, it's recording. So module list, it's recording, right? Hello. Yes, it's recording. So module list, and this has for self-taught code, okay, the I, that's it. These are the layers. It depends on the dot number of hidden layers, and the that's it. I think let's go to the forward function. It also has like out projection layer, because here you can see like linear output and final normalization. So out projection and dot linear confidence, right? This will have hidden states, positional embedding, and attention mask. Sorry, this will not have hidden states. It will have input IDs, positional attention mask, input embeddings, right? And then we have caching, which is going to be default is none. Input IDs. We can also define here self embed tokens, self dot and dot embedding config dot vocab size, and embedding dimension will be config dot hidden. Okay, so this is cool. And input IDs, input IDs will have a shape of batch, sequence, length. That's it. It will have this thing, batch and sequence length. So, and input embeddings, if it's passed from the forward call, then it will have batch, sequence length. So if embeds self dot input embeds dot tokens dices, it should not be d-type like this. Sorry, we are excuse me if I'm not defining or doing proper, like we are not defining the device and d-type and stuff, because I'm not taking care of that thing right now, just focusing on implementation and simplifying the implementation. But like later we can actually do that. We can use, but I think all good. There will be very less chances of the d-type mismatches, because I'm going to run this in CPU, and only on float 32 it will have a default settings and stuff, so it probably won't going to mismatch. If there is the mismatch, then we can actually fix that. So input embeddings, after input embeddings we have to, if attention mask is none, wait, first we have to put batch size, sequence length, and size is input shape. If attention mask is none, attention mask going to be dot ones, sequence length plus past scene tokens, because that past scene tokens we will get from dot get sequence length. And if cache is none, then cache is dynamic caching, right? Just making sure it will have get sequence, right? And yeah, and it will have like a d-type of input embedding, d-type and things. After defining attention mask, we need to build causal attention mask. How to build causal attention mask? Causal is basically for basic, we'd have to hide the tokens. So we have to hide the tokens from the origin, from the when the model will train. It's if it's trained, then we have to hide the future tokens. So because in data sets, when we train, we get like full sequence through batch size, and then the model can see the future tokens as well while predicting and then back propagating stuff. So we just hide it, the feature tokens, at each sequence, and it predicts at every steps. It predicts the next word, next word, next word, and the next word unlocks at every steps. So it creates like a triangular shape and something like that. So there's a function dot torch dot trio, which basically in a triangular shape it hides it, basically turns everything to zero, and that's what causal, that's how you can actually build a causal attention mask. We can use the pre-built stuff to build the causal attention mask. So after that, attention mask is defined. So causal is self-built causal, and this will have attention mask, right? This will have batch size. This will have query length. Query length is sequence length. This will have kv length. And now what is kv length? Kv length is, kv length is kv length. I'll define here. Kv length is sequence length plus scene. So this is kv length. And devices input embed device input embed dtype. That's it. That's how you define causal, and then we can use this causal. So for the linear attention, we need to use attention mask, and for the self attention, we need to use this causal mask, right? Then that's it. I think that's more of the initialization stuff, and then we have to do is for self dot layers, we can just define if self dot layer types. It has layer type, right? We have defined the layer type in the decoder. Okay, so layer type going to be if it's full attention, if it's, then use attention mask, else causal mask. And for the layer, we have to just define hidden state, positional embedding. What's the hidden state is, right? And positional embedding we will get from here. I don't think we can get positional embedding. And then we have this attention mask and cache. So mask, that's it. Positional embedding we haven't defined properly. We will define right now. First, this will give us the hidden states, and this hidden state is basically will be used in here, non hidden states, and then return, then hidden state, output check hidden state. So we need to return two things, because we will going to test this with the Hugging Face causal LLM or causal LLM class. So we will use our text model there. So we need to pass this hidden state as well as cache here. I have already defined some implemented some causal LLM thing where it will return logits, so we will use in a moment. So this is basically the text model, but here's one thing we have to do is we have to take care of the positional stuff. But I think we are not getting positional embedding, instead it's positional ID. We can just go and check it out with the model. It's in Qwen causal LM. This is we are going to use, by the way. And then we will define our text model here. Text model, text model which will come from 19th of exercise, and it has LM head, and this LM head will return stuff like this, logits and passkey values, and it will use our model. This is self-taught model. So it's attention mask, passkey values, use caching. Okay, these kind of stuffs we have to use in our forward. It's not positional embedding. Positional embedding we have to compute because we have rope implemented, so why we need to pass it. So it's positional IDs, and the attention mask should be here, cache should be use cache, right? So in positional embedding, if positional IDs is none, then positional IDs is basically torch dot arrange 0 to length and d type. We can just steal from here, and it will have a past scene tokens after this. It's weird, but like it will make sense if you think about like, okay, 0 to 20, this will create a position ID. Position ID is basically, okay, this 0 1 2 3 4 5, so the fifth token may have like the fourth position ID. The first token have 0 with the position ID, and third token will have second position ID. So it's from 0 to like sequence length. So if we already have some cache or like past scene tokens, so it again going to compute from 0 to sequence length, but we already know some past scene tokens already there. So let's suppose 20 sequence lengths is already seen. So rather than, so it will create 0 to 20, 0 to sequence length, so it will add 20 there. So the first token will become like 20, so it starts from the newer ones rather than, because we are creating this thing, that's why like past scene tokens make sense to add after that. Then this is our position IDs, and then positional embedding, and that rope contains rope X and position IDs, where X has no kind of thing, but you can pass hidden states, input embeddings basic, and position IDs. That's it. We have implemented text model. This is all text model. This is done. But wait, we have to test it. There may be many bugs, and I guess there will be, because I think we have done so many mistakes, what I think. So it will take input IDs. So input IDs we can define as torch dot ones paths, and d type should be torch dot long, and then we have attention, right? Attention mask and position IDs. Attention, where is the attention mask? Attention mask can be none, position IDs can be none, input embeddings can be none. Okay, so this is all we need. Okay, zeros, dimension, size. Oh, we have passed something weird, which is config here. It should be config dot hidden size. Yeah. Embedding indices must be tensor dot not nen type. Input IDs, it should be not input embeddings. Okay, many mistakes we have done. Okay, it should be dot self dot. Okay, if it's none, if dot k self dot k, and okay, so we have defined the attention, but spend it like attention mask. This is just the attention mask, none, expand bats, and -1. This is same things for here. Position IDs bats, -1. Awesome. So we have implemented everything now, and it's working. That is great, but we have tested only in random numbers. So we'll just review quickly what we have implemented. We have implemented the gated delta net, gated attention, decoder, and RMS norm, rope, and decoder, and then the whole text model. So this is cool. Like, I think we have covered everything. And right now, because what I want to use is that I want to use this model, which takes all the weights, the actual weights of Qwen model, and run some prompts. So let's try this, because this will be cool. If that works, then our implementation is correct then. So for that, to verify, we can actually do python run. I have already created a run where it loads every kind of key and stuff. The only thing, we probably it will not work right now, because because our keys and stuff will not match, because we have just defined our own way, and the weights, the keys should not match with our implementation maybe. So that could be a problem, but we can try it out. And if this is a problem, we can actually tell codex to change the keys to match the actual way. Don't change the implementation, just change the key and all the stuffs, the variable names and the weights names, so it can actually work. So yeah, let's go then. Prompt. So So it will take a flag prompt where we can say hi. Let's see, it will going to load the model. Yeah, fetching 6 files, loading the model. I hope it's recording also. Yeah, as I mentioned, like size mismatch, model layers and stuff. There's always a mismatch and stuffs in 3.5, right? So what we can just say, like, to the codex that I am getting error, but this is getting a mismatch and stuff. Fix those. Don't change the architecture, change the implementation and stuff. Just fix. Okay, let's wait. If it when it figures out, we can actually try it out. But I think kind of a shape from checkpoint shape this and stuff. So did we change something in the config 128? Okay, so it says like it fixed the checkpoint loading blockers and stuff, and verified model now loads and runs. So let's see like what exactly it did. Stop. Oh, wait. There was one bug I also saw, which was which we did some typo. Basically, we did a mistake here, which was like we passed input embeds here, even though we just defined hidden states. So that changed to hidden state also. Missing keys is 0, unexpected key 0. Well, it's running on CPU, that's why like it's taking time. We haven't optimized this, and there must be like some other things. Okay, so hi, how you doing? It just said what we have just said, and yeah, and it did some kind of stuff here. We can again ask like what are the mistakes, why it is like not responding really good, why it is not I think maybe the checkpoint is not loaded correctly, or like there's some implementation issue. Can you check my custom implementation? No, what's wrong with mine? So it can actually tell what wrong we did here, like if there's some little details we did or missed, probably because a little detail can actually change something and alter the it can change some output, obviously. So codex did some cache management, it fixed some cache management which had some issue, but like still it's getting the it is working end to end, but like it's not predicting the it's not working like Qwen. But I had another implementation of it which has exact keys and exact values and stuff. It's basically Qwen text model which has exact kind of uh, variables names and stuffs and weights name, so it actually fetches the right weights there. What I think probably the issue must be that it is not able to load the all pre-trained weights. It must be missing some keys and stuff. And that's why, like, although you can still see like it's working end to end and it's decoded the right thing, even though we passed hello in the prompt and then decoded the hello also. So it's working somewhat, maybe missing some kind of checkpoints pre-trained weights, which probably we can look and codex can look and check it out. It's kind of like a really good way to understand the model by implementing it from scratch. And I think you probably learned something and you understood how things are working from end to end. And it was really fun to actually build and implement these things. I will leave all the source code and implementations of this. So it was super fun to actually implement this architecture, Qwen 3.5, and we will see you in the next video. We will implement more stuff like this. I hope you're enjoying. Bye.